All right. So this talk is going to be about static analysis of Android malware and what kind of cool stuff can we get out of it. And it's going to be very simple static analysis. So it's not static analysis of Windows binary where you get all sorts of magic to do with Android application. It's actually really get a ton of information out of that. So this project, the initial objective of that project was sort of revisit the academic static analysis of Android application that's been done in the past, but we felt like it was done with old malware and needed to be updated, and it was also not very deep as an analysis. So we wanted to go like find some more interesting stuff. We wanted as well to get an idea of differences between malware and legitimate applications. We wanted to be able to find correlation between malware samples. So just by static analysis, can we say that these guys are sort of the same? And we wanted as well, during the process, we said, well, let's try to get out some information about how those malware are created. So when they write the code or when they generate the APK, what kind of process do they use? So this is going to be really exciting, right? But when I talked to one of my friends last week, he said, well, this is going to be, how did he put it, really boring. This is kind of academic stuff, and this is going to be boring. So I'm going to make a deal with you. We'll just forget about what are the objectives, and we'll go with the presentation. But first, I need to ask all of those here that are actual malware writer for Android, please leave the room, okay? This is not for you. I don't want I want you guys here. So anyone writing Android malware, just the doors over there, just leave. And the reason why I'm saying that is, well, we've done analysis of Android malware, so we're going to laugh at you guys for the stupid mistake that you've been making, and it's going to be a bit awkward. It's like you're sitting right there, I'm not laughing at you, so just like leave the room. I'm going to also tell you what not to do when you write your Android malware. So I don't want to give you guys tricks, so just leave the room. And of course, outside, like the police is waiting to pick you up, so that's going to be ending. All right, so this is the plan of what we'll try to go through. We'll see how time goes, and if we need to cut some things. So I'm let's say I'm nobody. So just for you guys who know me, I used to be at Cégep Sainte-Foy as a researcher in cybersecurity. Now I'm a cybersecurity analyst with the Government of Canada. And this work was a joint effort with my lab at Cégep and the CSIRC, the Government of Canada. And a couple of shameless plugs. So this is Hackfest, so we are allowed to do that. At CSIRC, so the Cyber Incident Response Center of Canada, we're actively looking for a student for internship this winter. So data analytic guys, deep dives with those that have hands-on in malware and trying to figure out what's going on. So if you're interested, guys, just come and talk to me. We just finished Geek Week 4. It was really nice, and we're looking to Geek Week 5. So it's a 9-day event where we gather people. We do a lot of cool projects. So if you're interested in participating or giving us money for that, come and see me as well. And of course, so there's, like I've mentioned, Government of Canada at some point, so I need to put out a disclaimer. The government is not responsible for whatever is in this presentation. I'm here on my own, so I'm going to say all sort of crap. This is my crap. They're not responsible for data, result, for stupid idea, for bad joke, whatever. Okay, so this is just me right now. It's not the Government of Canada. So, all right, what is static analysis of Android malware or Android application at large? So an Android application is an APK file. It's an archive. So this is the good starting point. It's sort of a zip file. You extract the zip file, and there's a shitload of information just right there, ready for us to pick up. There's lots of files. There's a DEX, or maybe more than one sometimes, a DEX file, a Dalvik executable. So this is the code of the application. We're not going to touch that because this is complicated. Like you need to decompile the code and get Java code, and then that's complex. So we'll go with more simpler stuff. Then there's the manifest. So this is a file that describes to the system that's going to run the application what the application looks like. So what's the name, what's the what kind of version it's running, what kind of SDK it needs, the permission required, and so on. So a lot of text information. This is going to be interesting. And then there's also something that is awesome. It's a X509 certificate. So all the Android applications are signed by the developer, and the developer certificate is included in the APK so that the system can verify that all the files are signed. And also, when you update your application, it makes sure that the update is signed with the same certificate. And while there's a certificate inside the APK, there's a lot of information inside the certificate, and we'll see this in some detail. So we've done some experimentation. We've analyzed a bunch of malware and legitimate applications. So we took about 200,000 malware, and we took about 10,000 legitimate applications. We did static analysis on them, and then we looked at the results, we compared them, we cluster a bit, and so on. So we got 200,000 malware. They come from security vendors that are our partner at CSIRC. So they just give us malware. And the legit application come from Google Play. Now, of course, it's really hard to say this is a malware and this is a legit application. So what I'm saying here is whenever it comes from Google Play is legit. This is not going to always be true. There will be malware at some point, but hopefully not that much. And whatever comes out from our security vendors will be malware. At some point, they will give us a legit application that they detect as malware and so on, but this should not be too much. So we've shown our sample at VirusTotal and to see what sort of thing we had, and we're pretty confident that the data set is sort of good. So legit applications are legit, and malware, most of them are malicious. What is interesting, at least from an academic point of view here, is that the data set is fairly recent. So we stopped the analysis on January of this year, and most of the sample we used, the malware sample, were for either 2015 and 2016, so fairly recent. Well, right now I sort of understand that it's getting a bit outdated, so we would need eventually to redo this kind of stuff and see if our statistics are still roughly the same. So the information that we get inside that we'll look at inside an APK is from the manifest. We have lots of text-based fields. So what are the list of permissions that the application requires? What is the minimum version of the system it needs, the Android SDK version that it needs to run? There's the target SDK version as well, and the max or the SDK version, which is useless. The application version code, so it's the numeric version of the application. This will be interesting. There's the application version name, so you get a string that you can put whatever you want in this that represent the sort of the human readable version of your application. There's, of course, the name of the application. There's an application label. There's the package name of the application. So lots of text-based fields that a malware creator needs to put something here, and it's not going to be always something smart. And especially when he's trying to generate those malware, not randomly, but automatically. So he wants, like, he has one malicious payload, and you want to put it into all kind of in several applications and distribute them. Well, he's going to need to come up with values for those fields for each of those instances of malware. And in the certificate, we've got well, the number of certificates that are there. I'm not going to talk about this today. It's not really interesting. We got a file name. So the certificate is in a file name. This looks like stupid. It's actually quite interesting. Like almost all the legit applications are in the same. The file name for the certificate is always the same. But for malware, there are all sorts of different names. Each certificate has a serial number. This is not really useful. I'll talk a bit about it later, but it's not really useful. Each certificate has a signature, so this is interesting because it uniquely identifies the different certificates. So this is going to be helpful. There's, of course, a public key in there. There's a validity period. Now, at this point, we're going to get into sort of weird stuff and that can happen, or weird behavior that we're observing. There's a subject name. So whenever you create a certificate, you need to put a subject name. When it's HTTP or HTTPS or a website, the subject name will be the URL or the domain name or something like that. But for Android application, it doesn't matter. There's no verification done on the name. So you can put whatever you want, and it's going to work. But you need to come up with something. And there's also the issuer. We're not going to look at it. And for other thing that we've looked at is the file list. So how many files, which files are included in the APK, and the creation date. So I've mentioned that we sort of believe that most of our application or of our malware are from 2015 and 2016. And the way we do that is when you extract the APK, the files within the archive retain their properties. So we can pick the last modification date of a file. We use the manifest for right now, and this gives us an idea of when the application was packaged. Because usually whenever you package the application, you re-encode your manifest and package your APK. This is good enough for us. All right, so let's go with the manifest. Start with the application package. So every application needs a package name, and the rule for that, and what I mean by when I say rule is how Google Play handles those values is that two applications on the Google Play cannot have the same package name. If you have two applications have the same package name, Google Play says well, they're the same. And when we look at the statistic, we got almost one package name for legitimate application, so one different package name for every legitimate application. So we can assume that we have multiple versions of the same app a few times, like 10 times. But we got only one package name for two malware. So the malware are reusing package name a lot. And obviously, I'm going to come back with this during the presentation. They don't care about Google Play rules because eventually they're not going to push their malware on Google Play. Some will, but most will be distributed through other markets. So they don't care what rules are on Google Play. They just care, will my malware get installed on the device? So a lot of reuse in the package name. Actually, in our malware data set, we got one package name that comes back 34,000 times. So it's a lot of reuse for the same package name. We also have one prefix that comes 7,000 times in our malware. So they're all different, but they always have the same prefix. And this is sort of interesting when you dig into that sort of data. So we can get this beautiful chart. The big blue bubble is all the application that have the package name of a com, young run, blah, 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 which happened 33,000 times. And then we've got all sorts of other smaller clusters that we could look at, and some that can be eventually merged because they're really close to one another syntactically. But we can also, what we need to get out of that as well is this is going to eventually skew our data. Like there's 33,000 samples that we could think of right now, they are the same. So they're a variation of the same. So this is eventually going to skew our data. So whenever we look at stats, we need to keep in mind that we've got lots of repetition in our data set, but that's what we wanted. We wanted to have a representative overview of what's going on in real life. And so just before I go any further, when I say a sample, what I mean is an APK that has its own MD5 hash. So whenever you take an NDK, you hash the file, it gives you an MD5. If they're different, then for me, they're different samples. They could be pretty much the same application with a different icon, but they will hash to different MD5, so they're different samples for me. So we don't know right off the bat that they're different or they're the same, so we need to analyze them separately. Then there's the application version code. So here we see a bunch of interesting things. So first of all, application version equal 1. We've got nearly half of our malware that use application version equal 1, and only 14% of legitimate application. And the reason is, on the Play Store, whenever you push a new version of your app, you need to increase the version code. Okay, you absolutely have, otherwise you won't get there. Since malware don't care about updates that much, then they put version 1 and it never gets changed. All right, so this is one interesting thing. So version code equal 1 is weird. Then there's those values, 2,100,000,000 and 2,100,000,000, 147 million, and so on, blah, 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 the one at the top, which occur like Both of them, it's a 3-4% in malware and almost none. Like we got 1 instances and 6 instances in legit sample. So this very high number here used, okay, right now, the maximum version code you can push to Google Play is 2,100,000,000, all right? So if you try 2,200,000,000, it won't make it. So a legitimate application cannot have those high values. But in the past, the maximum was 202,147,000,000, blah, 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 so the value at the top. And a few legit apps made it to the Google Play Store before they changed that value. And for some reason, a fair amount of malware used that specific value for their version code. I don't know why they do that, but really there should be a value somewhere. Like 4 would be a good app version code for a malware. That's what I'm saying. All right. Then there's the minimum and target SDK version. So on which system will the application run? All right, that's basically what it says. So we got nice graphs with like colors and malware are different than legit application, but let's forget about that and let's look at this guy. So target version for malware, target SDK version higher than 25. So remember that this was done in January of this year, and at that time the highest SDK version for Android was 25. So we got a few values for malware that are higher than the current greatest SDK version. So actually what we see is 26, 27, 30, 42, so, and 999. So some guy is doing a malware that will run very nicely in future Android versions. So whenever your Android phone can teleport to you, this malware will work as a charm. So this is cool and this is easy to spot. Like it's sort of a mistake that you can spot easily in malware. Then there are the list of permission. What permission are required by the application or the malware? And this we see that all the time, at least I do. The comparison between the popular permission for legit and malware. So they're different. A bunch of permission indicate malware more than legit. But what we found very interesting on permission is a lot of malware, more than half the malware, have in their manifest duplicate permission. So they request twice the permission, let's say, give me access to internet. And this is really interesting. It happens a little bit with legit app, but much less. And what we believe happens here is, so you got a malware, now you got a legit app, you get a malicious payload, and you want to package your malicious payload into that app so that everything will run. So you take the app manifest and you add the permission that you need for your payload, your malicious payload. You add that to the manifest, but you don't do like all sort of complicated stuff like, is this already there? Like I'm going to do a set and it's going to remove the duplicate. You just put it there, and if there are duplicates, the system don't care. It works anyway. So we believe that this is an artifact of automated repackaging of malicious payload into normal Android application. And there's a lot of duplication. It's not like internet is always duplicated. Like some malware have like dozens of duplicate permission in their manifest. So it's really interesting. For the legit, we believe it's more something like two developers manually have the permission separately, and then when they commit, it doesn't get merged properly, but this is just like a wild guess, and we don't really care that much what they do. So let's move on to the certificate part, all right? So serial number, there are two certificates that are very special in Android, the debug one and the platform test one. Of course, you can never push an application that is signed with those certificates, but malware don't care, so they do use those certificates a bit, which is weird, like it's sort of easy to spot. We found also some quirks. So serial number, when you generate a certificate, you need to pick a serial number, or it's picked automatically for you, and the goal is that this value will be unique across all the certificates and sort of magically. Of course, it doesn't work, so we've picked a bunch of serial numbers for which we see in more than one different certificate. So two different certificates share the same serial number, so the conclusion is serial number doesn't really uniquely identify certificate. So we need something else. We're using signature. So regarding signature, so the signature of the certificate itself. So for legitimate application, the number of distinct signature that we see is fairly high. So it's 85 out of 100 for different certificate versus number of application we have. For malware, it's much lower. We're at this sort of 0.6 rate or 60% rate or whatever. So they reuse certificate much more than legit application. So legit application, you reuse a certificate because you want two of your, so if I'm a developer, I'm going to sign all my apps with the same certificate so that they can interact together better inside the system. So under it, there's a sort of a special channel, communication channel between apps that are signed within the same certificate. So it makes sense for a developer to sync all their apps with the same certificate. So that's why we got some amount of duplication. For malware, it doesn't really make sense unless you want them to interact, which, well, in some cases would make sense, but there's way too much duplication for that. We found like one certificate that is used to sign more than 10,000 samples in our malware data set. So when you see that, you get one certificate signing multiple samples, then you're fairly sure that all those samples come from the same place, all right? So it's not working anymore. All right. So same certificate means, implies-ish, same origin. There's some cases where that might not be true, but this is for mathematicians to figure out. But if you have different certificates, it doesn't mean that it comes from different places. And this is going to take us a bit deeper. So the next step is, all right, we found 14 malware samples that have distinct certificates, but all those certificates use the same public key. And, well, obviously the same private key. So they're most likely coming from the same place. So the guy, for each sample, he generated a new certificate, but he went through the trouble of reusing his old key to generate each new certificate, so he would make sure that it would be easy for me to spot him. So thanks, man. That was fun. Now, there's the subject field in the certificate. So who the certificate belongs to, let's say that. For legitimate application, we got almost a one-on-one correspondence between the number of different certificates we see, the different signature, and the number of different subject name we see. So roughly one-on-one, not quite there, but for malware, it's 1 to 2. So subject name gets reused twice as much as certificate themselves. All right? So this is interesting. We can see a bunch of examples here. Very generic one, yes, 35,000 times. So this is probably our big cluster that we've seen earlier. So they use the same package name and they use the same subject name. We've got the unknown, but I'm from China, 20,000 times. Unknown, 2,000 times. I don't know what this is. Yeah. Maybe it means something. Maybe it means unknown in an unknown language. But this is fairly common, like 4,000 times. And then there's the LLPFIHAGYDEAK, blah, blah, blah. That comes back 3,000. So this is very specific. This is probably a random generated string, but it's the same on all the certificates, right? So very interesting. Sort of easy to spot it and say, well, I'm going to look at those 3,000 malware. They probably come from the same guy, or at least from the same place. Certificate file name. So let's not bother with the top. Let's go here. So 84% of legitimate application, the certificate file name is called cert.rsa. All right? So if you do a malware, just call it that, and I'm not going to see it. For malware, it's 42%, so much, much less. So some of those figured it out, but a lot didn't. There's 17% zzw.rsa. Like it stands out. zzw, it stands out. This is, again, the big cluster of 33,000 apps that we've seen since the beginning. So file name is stupid, but it's really interesting. And there's another thing that is cool with that is we have a bit more than 2,000 malware sample that use a pattern of 8 digits .rsa for the file name, and 8 digits for RSA, 8 digit .rs or whatever is to me year, month, and date. All right, so it's a date. Well, not calendar date. So what we've done is we've compared those file names with the creation date of the APK, and surely enough, 1,600 of them, the certificate file name match with the creation date of the APK. So this is nice. Now we get a better understanding of how their process works. So they generate the certificate automatically for every time they want to package a new sample. They choose the name for the certificate file, which is the current date, then they package their application. We're trying to see a good insight into how their process works. All right? We're going to come back with some of these things later on. Another thing that is cool with certificate is that you have a validity period, so a start time and a end time. All right? So usually for HTTPS, this means if you go to see a site and you get a certificate, you want to make sure that your certificate is not expired and has started to be valid, all right? Otherwise, you get an error. Chrome says, well, you shouldn't go there. And Internet Explorer says nothing. Just saying. But for Android, the system, the actual system doesn't care at all with the date. Google Play cares about the date, but the system doesn't care at all. So you can have a certificate that is already expired. You'll be able to install the application on your phone or your device, but you won't be able to make it to the store. All right? So there's a bunch of rules to be accepted to the Play Store, but they don't matter for malware creator, so they don't necessarily follow them. I guess they should, but they don't. So the certificate of an app must not expire before sometimes in 2023. And the certificate must have started its validity period when you push the application. But they can still be installed on a device if you don't go through the process. So we've used two strategies to leverage that information. The first one is, what is the actual validity period? So what is the delta between the end time and the end date and start date of validity? And what we've seen as data is two completely different worlds between legit and malware. So in the legit world, legitimate application, the minimum value of validity period is 18 years, all right? And actually, what is suggested to developers from the Google Play Store is use 25 years, all right? So sort of a long scope. For malware, the minimum value is 1 day. So they really don't care about the validity period. It's going to be installed anyway, even if it's not valid anymore. And let's say the average for malware is 10 years, and for legitimate application is 189 years. So there's a huge difference between validity period of malware and legitimate application. And this is something that we can look at it very easily, and that you guys, when you write your malware, you should be careful with that. The second strategy, I'm going to talk a bit more about that later, is the difference, the delta between the start date, the start date of the certificate, when the certificate starts to be valid, and the date the application was created. Is there a sort of a delta between those two? I'm going to come back with this whenever after I've talked about creation date. So well, I mentioned it a bit earlier. So creation date is we extract the archive, we pick the last modification date of the manifest, and we say this is the creation date of the application. Now, it's not 100% right, okay? For two reasons. We've got a bunch of applications that were created before 2000, okay, which is weird for Android. For those who don't know, it wasn't there before 2000, all right? And we also have it's not always clear that the manifest will be re-encoded when you generate your APK. So sometimes the DEX file is a bit more recent than the manifest. So we'll eventually need a better algorithm for that, but let's not bother with those details. Let's assume that this works fairly. And what we can see is that the malware creator, like the legitimate application creator. They work mostly Monday to Friday, create their apps, and they do something else on the weekend. Or you could say, well, they write one legitimate application with one end and the malware on the other end, and at the same time. So different ways of seeing that. But creation date is sort of interesting. Now, if we come back with the delta between the creation date and the start of the validity period of the certificate, this is weird. And we look at those values with second level precision. So like the delta is 1 second, the delta is 2 seconds, the delta is 6 hours, 23 minutes, 3 seconds. We get that graph. Now, this is an awesome graph. So the values are, the x-axis is hours, and the y-axis is the number of malware samples. So what jumps at us, or should, if you haven't yet figured it out, is that we're on the clock at hours, 12 hours. A delta of 12 hours between the creation of the APK and the start date of the validity of the certificate. 12 hours plus 1 second, 12 hours minus 1 second, there's a cluster there. 13 hours, sharp. 8 hours sharp, 7 hours sharp, 6 hours sharp, 5 hours sharp, 0 hours sharp, okay? So we're on the clock on the hour. This is really, really weird. And this is gonna suck, but I don't really have a smart explanation for that. My guess would be that the certificate is created on a machine, and then the code and the certificate, blah, 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 is shipped on another machine, like package your malware as a service, and then the APK is created there, and the other machine will be on a different time zone. So there's going to be an hour gap, a few hour gaps between those times, with maybe sometimes 1 second because we've got a network glitch that took us longer to upload our stuff. So this is something that I'm looking for a smarter explanation to that, but this is data that is really interesting to look at. Then there's the file list. I'm going to just point two things here. The first one is that the number of files in a legitimate application is much higher than the number of files in a malware, which sort of makes sense. Like in a malware, you don't expect them to provide you with icons for all different screen sizes. They just want it to run and infect your system, so you don't care whether it looks slick or not. So the number of files is quite different, sort of a ratio of 2 to 1. And there's a lot of malware that when you unpack the APK, what you find inside is a bunch of files, dex file, manifest, certificate, and another APK. And this is interesting because from the outside APK, you can go and run code that is within the sort of embedded APK. So when you do analysis of malware, static analysis of malware, then you need to go through all the levels to get probably the code that you're looking for. But it's interesting. And there's a few legit that do that as well. Not too sure why yet. All right, so now we've got lots of statistics and data, and we sort of had a few laughs about mistakes that they do. What can we do about it? Can we say, well, these malware, they're from the same place because they're just too much alike? So I've got 3 cases to show you. So the first one, we pick one sample with this MD5, and we want to know what can we do about it. Of course, it's all pre-cooked, right? I did it before. I know what's going to happen, but you don't. So we've got 14 APKs that are grouped together with these tabs. So what we've done here is we've taken each feature that we've extracted, and the bubble is a specific value for that feature. The larger the bubble, the more APKs have that value. So for app name, I'm going to pick one that's going to highlight. So for the certificate file name, all the 14s here use the same file name. It's cert.rsa. They all use cert.rsa. There's more than 100,000 malware that does that. For the application name, they use com.uusafe.wrapper.application. There are 19 malware that does that. We've got a cluster of 14. So this is sort of a bit more focused. And what we have here is they all use the same public, like those 14 use the same public key in their certificate, and they're the only 14 that does that, okay? So at that point, we say, well, guys, we got you. These are together for sure. They're from the same place, from the same guy, or from the same organization, or something like that. So they go together. They might not at all be the same malicious behavior, okay, but they come from the same place. So it's the same cases. This is a sort of a dump of our database. Can you see anything on that? Or I'm just going to highlight you. If it's not a problem if you can't read that much of what's there, because I'll go through what's important. So we've got 14 samples that were created across an 18-month period. So it's quite a long span for so few samples. This is interesting. The validity period for the certificate is always 1,000 days. Okay. So I forgot to mention something about the validity period. The reason why it's so low for malware and so high for legit is when you package your legit application through Clips or whatever IDE you're using, the default value it gives you is 25 years. It's in years. So you say 3, it's 3 years. If you leave the default value, it's 25 years. When you're a malware writer, you don't go through that pain of using an IDE. You generate your stuff automatically from the command line. Maybe you're using a tool like OpenSSL or whatever. And when you specify the validity period in that kind of tool, those kind of tool, the default value is days. So if you enter 3, it's going to be 3 days. So that's one of the reasons why it's so unbalanced. Okay, case number 2 is a bit more difficult to see. So we've got, again, a bunch of big bubbles. So we've got 277 applications or malware samples that are clustered with the same app version name, all right? So they all use cert.rsa as a file name. Well, they all do, so we don't care. They use 7 as the mean SDK version, but lots of them do. They use 10 as the target SDK, but a bunch of them do as well, so it's hard. They use 19 and 20 as the app version, but a bunch of them does as well. And they use 92.0 for the application version name, so that's a string, and only 277 do that. But it's not really hard evidence enough, so 92.0 is sort of like, I can put that in my application, and you can put that in your application, and we haven't talked to each other. So if we dig a bit more in the data, we see that there's 8 different values for the application name, and they all have the same pattern of com.4-letter, 4-letter, 5 letters in lowercase. If we go with the creation date, it spans from, it's a month span, so from February to March of 2016. So there are 277 applications clustered into that space, or that time. And if we take the application package, now this is going to be cool. We're going to play Scrabble with malware. So I'm going to blow this up a little bit and give out with my punch. So these are the big bullet. The black bullet are the actual package name, and the sort of empty bullets or indented bullets are the word that originated from the package name. So they picked word, all starting with the same letter, and then they added randomly a bunch of letters into that, so that casually become castually, cattle become zadl, and ceiling becomes feel. So like they're playing with words to, I guess, throw us off or something, I don't know. But then when you look at that data and you see the process behind it, it's fairly clear. I don't think that a lot of people will do that kind of game in their basement independent of one another. So to me, this is from the same place, okay? Case number 3 is also interesting. So now we're getting a larger cluster. So 7,223 malware sample, all started with the application package starting with the specific prefix com.ym.refpackage.gxyq. Not dot, but something else at the end. The something else is different for every sample, but the prefix is always the same. So again, min version doesn't mean much. Target version doesn't mean much. Certificate is temp.rsa, so it doesn't mean much, but actually it's pretty only those samples that use that file name. So it's quite interesting. The certificate subject, well, this one is cool. They almost all use the same, and then there's a bunch of different things. So we're gonna see data differently. Package name, so it's the prefix that I've mentioned. The app label, it's always a prefix, and then VIP and 5 number. So a huge pattern you can see here. The subject name, so we've got 6,700 samples that use XX, 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 and Shuani as a subject name. And the other, all the others, so we've got like 600-ish others. They use a pattern, so they're random and unique, but they use a pattern of 2-letter, 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 7-letter. Okay, and then the certificate file name, most of them, the exact same numbers, 6,706, use temp.rsa, and all the others, they use 5 capital letter .rsa. And if we throw this data into a timeline, what we see, so I'm going to jump off the stage here, and actually I got it behind. So the first line here is the cut between the subject name. So prior to that line here, subject name was the same. And after that line, which is, the date is October 31st of 2016, they changed the way that they generate the subject name for their malware. They also changed the way at this point that they generate the certificate file name. So they went from temp.rsa to 5randomletter.rsa. And a month later, 1st of December of the same year, they changed the way that they generate their application label. So they went from VIP 5 number to something .5 number. So they dropped the VIP, less obvious. So now we can follow the evolution of their, generation process for the malware. So at this point, we say, well, you guys, we can follow you enough that we know you're from the site. So I think I'm running a bit late. 5 minutes? Oh, okay, good. So we're going to see, I made just for you a super crazy dashboard with a new technology that's called HTML, where we can sort of visualize or navigate through the cluster. So we just pick one feature. Let's say we'll start with signature. And we have, these are all the values we see for certificate signature and all the clusters. So we've got, first line here is a cluster of size 142, a cluster of size 2,119. So let's look at this one. So this is all the feature for all the samples into that cluster. And we see that they all use the same value for most of the field, except for not valid before date, not valid after date, and the validity period. So there's something here that changed. We've got 2,000 samples in that cluster, and we've got 2 different not valid before date value, okay? So we've got a very, very strong feeling that they are indeed the same, from the same place, because all the values are the same. All right, let's come back and see another one, maybe a subject name. Memo sounds cool, so we pick another one. And we see that, well, this one has fewer fields that are the same, but we can, again, get a good overview. Well, they use all the same certificate stuff, so right off the bat, they're done. This is coming from the same place. But they use the same version of target, they use the same label, same application name, and so on. And we have another one that might be interesting. See, this comes back to me on Taipei that I cannot read those. And we see that they use the very same subject, but they change the certificate. So we've got a cluster size of 140 that use always the same subject name, always the same not valid before, not valid after, and always the same validity period, which is a odd number, 20,081 days. That stands out. No, sorry, that's not the value. So it's 125 days, and we've got 20,000 samples using that value. All right, so so there's a lot of clustering to be done with those values. So conclusion, so we've got some weird, so we can easily extract weird stuff or interesting stuff to do correlation. It's low-hanging fruit. There's weird stuff, APKs inside APK. There's the 12-hour gap. There's duplicated permission. This is weird. and so the conclusion is, so we can do easy clustering. Is this a bad thing or a good thing? So, well, it's good news because it's fairly easy to wrap them all up and do something or detect them or whatever. We can get better easily. But it's also bad news because if it means that it's so easy, then they just don't care because they can get away without doing any hard stuff of, picking a different name for each of their malware. So I guess we're pretty much done, or if you have a few questions, I'll try to evade them as best as I could, or I'm sticking around for 2 days so you can grab me to have a chat about that. Sorry.